Hello, everybody. Welcome to my talk. Nice to see many people in here. My name is Manu, and I'm gonna talk about using deep learning for gender identification of tweet authors. For those who don't know me, I'm 25 years old. I started working in Knowit last year, right after I finished my master's thesis from NTNU, where I specialized in artificial intelligence. So my thesis is what I'm going to talk about today. It's called a deep learning ensemble approach to gender identification of tweet authors. Kind of a complicated and heavy name. Yeah, and I worked on it with a friend of mine. Yeah. This is the agenda for today. I'm going to start out by talking about author profiling and natural language processing before I move on to giving you a brief description of supervised learning and neural networks. Then I'll go on to talking about the problem we wanted to solve. Then I'm going to go into how we represented data in our different models and the model architectures before towards the end, will show you some results and a qualitative analysis, by which I mean showing you some examples of the predictions made by the models. And then I'm going to conclude by talking about lessons learned. Now, author profiling is about identifying characteristics of authors, like age, gender, nationality, and other things, based on linguistic features found in the text they write. Now, there are several applications, like, for instance, marketing, where it can be useful for companies to identify the different types of people who like or dislike their products or services based on, for example, articles or reviews. Also, it can be used in forensics. Forensic linguistics is a branch of applied linguistics where linguistic knowledge is used to, with regards to law and criminal investigations. I don't know if any of you have seen this series or heard about the Unabomber, which was an actual terrorist in the 70s, 80s, and 90s. Spoiler alert, a part of capturing him was using authorship analysis to, or what they did was compare a manifesto written by the Unabomber and the letters written by a suspect, and they saw that this is probably the same person. Now, natural language processing concerns the task of programming machines to be able to process human language. So typical tasks include speech recognition, natural language generation, and natural language understanding. Author profiling goes under natural language understanding. How many people in here have worked with machine learning before? And a couple more people, right, who were at a workshop yesterday, right? Okay, that's good. So most of you probably know what this is all about, but I'll give you a brief description anyhow. So given a problem you want to solve, something you want to predict, you create a data set with examples from the problem space. You feed these examples to the machine learning algorithm. And then you also give it the answers to the examples so that it can find patterns in your data set, which it can then use to generalize the problem space and then hopefully predict solutions to new examples which it has not seen before. It's a simple concept, but there are many factors here which can affect the result. So the machine learning algorithm that we used in our project was artificial neural networks. It has been quite in the wind lately. You hear a lot about deep learning, which as it is today, it means a neural network with many layers. This is how a neural network can look like, a simple one. You see it has an input layer, a hidden layer, and an output layer. And those circles, those nodes, are called neurons. And the reason why it's called a neural network is because initially this was based on the human brain. The human brain contains neurons which process information, and they transferred, or they use this analogy for artificial neural networks. So the number of neurons in the input layer reflects the number of features which you use to describe an instance of data in your dataset. And the number of neurons in the output layer reflects the number of prediction classes. So in the case of gender identification, you have 2 prediction classes, male or female. Question?
Why is what's it called the hidden layer?
All right, so the question is, why is it called a hidden layer? All right, that's fine. No, it's a great question. I was actually going to get to that. The hidden layer is called, it's called a hidden layer because you don't actually know what the what the neural network is able to find in your data set, right? So the patterns that it finds, it's hard to know exactly what it is. And the hidden layer is actually where the magic happens, right? The network can have many hidden layers, and each hidden layer can also have an arbitrary number of neurons. And these are, we call it hyperparameters, which you have to experiment with to try and figure out what number you have to choose to get the most optimal results. So in each neuron, a function is applied to transform the input, and that's a vital part of the machine learning process. So during training, these neurons will hopefully find different features or patterns in your data set, which together make the basis for the output prediction. So the goal of this project was to train a classifier which, given a tweet, can output the gender of the tweet author. Now this might sound a little bit strange at first, because people are different, people write about different things, and is this discrimination or what's going on here, right? But the thing is that for the past 40 years there have been several linguistic studies which show that you can actually distinguish the gender based on numerous factors like the topic and the content of the texts, but maybe more interestingly, the writing style. For studies show that women tend to be more involved in their writing, with the greater use of pronouns to close down the gap between themselves and the reader, while men tend to be more informational and they maybe try to distance themselves actually from the reader. But such indications may change over time, right? Some of these studies were 30 years old, and society changes and all that, but we decided to give it a go and see if we could find something. So our training set contained 650,000 tweets. The good thing about tweets is that it's easy to get a big data set, right? Because the tweets are available online, and you can just scrape Twitter. The problem is that the text is very informal. Many tweets contain a lot of mistakes with regards to grammar and spelling, and we'll see why that can be a potential problem. So the training set included the validation set, which was used to see how well the model could perform on tweets it hadn't seen before, right, during training. And the test set was used as a final evaluation of a trained model. We trained 3 different models in this project. Each of these models used different representations for text and also different neural network concepts and architectures. And then finally we created what we call a stacked ensemble classifier. Basically, it just combined the predictions of each of the 3 models. So in what we call the document level classifier, we represented tweets using something called bag of words and n-grams. And what that I'll try to explain what that is. Say you have 3 different sentences, and you need to represent these in a way that a computer can understand, right? Because text it doesn't mean anything, right? So you need numbers. So what you can do is you create a dictionary or vocabulary containing all of these words, and then you associate an index to each word. Because then you can create a vector representation of the sentence where each value corresponds to the number of times the word appears in the sentence. So we created a dictionary containing the 10,000 most frequent words and n-grams in the training set. An n-gram is a sequence of n words, where n is a number. So instead of only counting single words, you can count the number of times 2 words or 3 words occur together in a text. Now the disadvantage with this representation is that it disregards the fact that the order of words matter in text, right? So this representation only captures the fact that these words occurred in this text somewhere. And that's why we called it the document level classifier, because the model captures very high level patterns. This is a diagram of the architecture of the neural network. I'm not really going to get into the details of it, but it's actually pretty similar to the example I showed you earlier. And here you have 10,000 input neurons in the input layer because we use 10,000 words in the vocabulary, so each data sample contains 10,000 values. In the word level classifier, we did things a bit differently. Here a tweet is treated more as a sequence of words. As a representation, we used something called word embeddings, which are vector representations where the relationship between words are captured. So with this technique, semantically and syntactically similar words will appear close together in vector space. So if you graph it out, you'll see that similar words are closer together, which I'll show you in a moment. There are many different types of word embedding methods, and the one we used is called GLUB. And we used a set of pre-trained word embeddings which were available online, so we didn't train our own embeddings. So in this case, the so-called vocabulary will be the set of available word embeddings. So over the years, there have been many different techniques for creating word embeddings. But back in 2013, this particular one got a lot of attention because it was very efficient and usable. The one we used, called GLOVE, came after that one. So the figure to the left is a subset of a larger graph. And here you see that all these words has something to do with, family and relationships. And so you see that they're clustered together. So in the larger graph, you'd see that other forms of words will cluster, more distanced from these words. And similarly, in the graph to the right, you see that countries are clustered closer together, and then you have the associated capitals not far from them. The disadvantage with this representation is that only words available in the set of pre-trained embeddings will be processed by the model. So if there's a word that appears in our dataset which is not in the vocabulary, it will just be disregarded. So this is the word level neural network architecture. It's a little bit different. I'm not going to go into the details, but here we used something called an LSTM, which is a recurrent neural network. It's different from the one we saw before. But what's important to know is that recurrent neural networks are better able to handle sequential information in data, such as, the order of words in a sentence. So in the last model, we took it even further. We treated a tweet as a sequence of characters. So essentially, we broke down words to even smaller building blocks. This bypasses the limitation of the word level model because now you can create a vocabulary which contains characters that occur in your tweets. And it's a lot easier to make a mapping of this because there aren't that many characters in the English language which you use in text, right? The character level neural network turned out even more complicated. Here we also use a recurrent neural network, but in addition, we used a convolutional neural network, and all I'm going to say about that one is that it is usually used for images because they're really good at capturing shapes and objects in images. But it turns out that you can also use it for text. So after creating these three models, we wanted to leverage the fact that it could be possible that the different models are able to capture different linguistic features in text. So we created a stacked model where we combine the prediction using an aggregation function so that you can make a collaborative overall prediction, if that makes sense. So we tried different aggregation functions. In majority voting, each model outputs a prediction, and then that prediction counts as a vote, and then you just base your prediction on the majority. It is also possible to see how confident a model is of its prediction. You can see how strongly it believes the author to be male or female. So that's why we tried out another method called maximum confidence, where we essentially let the most confident model dominate the entire prediction. On to some results. These are the prediction scores on the test set which we used. And what you'll notice is that the scores are quite similar. There aren't a lot of difference. The stacked model performs a little bit better than the other models, but not by much. Another thing is that if you want to guess the gender of an author, you can just randomly guess, and you're going to have a 50% chance of success, right? So then when you look at these numbers again, they're not really, they're not really that impressive, right? But at least it's a little bit better than random, which means that the models were able to learn something. And the thing with machine learning algorithms, as I said, is that it's difficult to know what are they able to learn, right? But we decided to look into this too by looking at some of the results. So this graph shows you the most frequent words occurring in both correct predictions and incorrect predictions. And well, the thing is that we're a bit uncertain about some of the words because they just don't make sense. Like why does the word male and Tina appear a lot in the dataset. Uh, but if we look at the other words, you'll see that in the frequent words occurring in correct predictions for male authors, you'll see words like league, season, soccer. They're sports-related terms, right? And similarly for females, you see makeup, love here. Um, so evidently, there's a pattern here where the system is very oriented around content, and also it seems like it's drawing on some stereotypes here, right? And then, where it gets interesting is that when you look at the wrong predictions, where the author was actually female, but it thought they were male authors, you see words like Google, business, basketball, player, scoring, which, females can be interested in those things too, right? But the model wasn't able to catch that. It just assumed that if the tweet is about sports, then it's got to be a male. So, these stereotypical observations just makes our model look like a man chauvinist, I guess. And, further investigations actually supports this notion. These are examples of tweets which were predicted correctly by all models. So for the female author tweets, you see gorgeous dress by my favorite designer, and I'm finally wearing dress clothes to work. LOL, I gotta go shopping and start wearing heels. So yeah, you see the point, right? And then you see that the language is also very informal. Take notice of that. And then yeah, the male tweets are about gaming and football. Question.
Hadde blitt bedre,
Eh,
hadde blitt bedre hvis du hadde lengre tekster. Altså du konkatenerte tekstene fra en forfatter.
So the question is, would maybe the results be better if you had longer texts, right? If you combine the text so that one text is all the tweets by one author, and yeah, I think it is a problem that the tweets are really short. That's a huge problem, actually. I think, which I'm going to talk about later as well. But yeah, I'm gonna get back to that one. So we were all right. So the first tweet there, you see that it doesn't really make sense, right? What does that even mean? That is also one of the problems in our data set, is that there are a lot of tweets which look like that tweet. It's just a random information about nothing. And those tweets, cause a lot of problems for our models because there's no information to actually capture there, right? Then you see the two next tweets. They were written by female authors, but they were classified as male. They're about football. It's not able to understand that females can like football, right? And then similarly, you see in the tweets written by male authors, it's about makeup and clothes, and it just doesn't get it. So what we can infer from this is that it's likely that most of the tweets about sports were written by males in our dataset, right? And vice versa in the female case. If there is a mention about makeup, stuff like that, there were a lot of tweets about that by females and just a few written by males. So our models were not able to capture writing style as much as we'd hoped for, and instead they were biased towards the content of the tweets. So lessons learned. I think a huge problem in our project was that the data set was, it wasn't really good. Bad quality data. I haven't talked a lot about pre-processing. We did do some pre-processing, like, lowercasing tweets and replacing all those hashtags and URLs with placeholders. But I think what caused more of an issue was the fact that we had so many tweets just containing random information about nothing, and also the fact that there were a lot of short tweets. Some of the tweets were just one word, you know, LOL or something. It's not possible to see which gender the author is from LOL, right? And we did remove many of those short tweets, but I think we should have explored that area a lot more. And then there is the fact that tweets are just short anyway, right? Maximum 140 characters. So it could be that it's just impossible to like capture linguistic information from such short texts. But I think you'll have to explore more to actually know if you need to have better control of your data. Data is like the foundation of a machine learning process, because if there's not useful information in there, the algorithm can be really good and it's still not gonna find out anything, right? We also found many non-English tweets. There are like Spanish tweets, Dutch tweets, and Norwegian tweets even. And we initially thought that the whole data set was English, but turned out it wasn't. And we used some language detection software and stuff to remove a lot of those tweets, but then you end up removing some English tweets too, right? So it's difficult to find a balance right there. Yeah, I think that was it. Questions? Tired? Looking forward to dinner? One question. Yeah, so we didn't scrape tweets ourselves because there is something called a pan shared task competition where basically they provide the data sets already labeled, and then people create a classifier and there's a conference and they talk about that stuff, So the data sets were already labeled. Probably, because I don't think you can. I'm not sure if you can fetch the gender of an author using the Twitter API. I don't think you even have to provide gender on your profile, right? Maybe you can fetch it if it's provided, but otherwise not. I'm not sure. But if it's not provided on Twitter, then if it's not provided on the profile, then you're not gonna know if it's a male or a female anyway, right? Anything else? Nope. Then we're done. Whoa, 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 whoa.
Jeg tenkte på det at det er jo på en måte litt selvmotsigende å lete etter tekstmønster i noe som skrives å være så kort som overhodet mulig. Det ligger jo i sakens natur. Man skriver ikke sånn som på en måte deres naturlige tekstmønster er. Nå skriver jeg veldig kort. Hva hvis dere hadde brukt det på lengre tekster? Har dere prøvd det?
All right, so the question is, when people write short texts, then they're probably not going to write as they usually do anyway, right? So why didn't we try this on longer texts? So one thing is that scraping data, like we could have scraped news articles or something like that instead, or blogs. All that takes time, and since we could just use these data sets, we thought let's try those, right? Because then we can skip all that work, and also we thought we could maybe enter that competition as well, right? Because then you would have to use that data set. But most likely, I mean, people have done it before, analyzing longer texts, and surely it works better. There's more information in a long article than in a short text. Exactly. All right. Did you have a question? All good. Thanks for coming.